Section 4.2, we're going to be talking about graphing polynomial functions. So the objectives here is to be able to graph a polynomial function, use the intermediate value theorem to determine whether a function has a real zero between two given real numbers. It says if p of x is a polynomial function of degree n. So before we go any further, I just want to talk about p of x here. The p here is the name of the function. We're going to call it p, and it's in respect to x. So p of x is going to give us an outcome for y. So sometimes you see p of x, sometimes you're going to see f of x, h of x, g of x. I just wanted you to have an understanding of why they called it p here. They're saying polynomial functions. It says we're going to have a degree of n. The graph of the function has at most n real zeros and thus most n x-intercepts. So what is it saying? It's saying that whatever, okay, first things first, we're going to write our function in descending order. Okay, order. So that means larger power to smaller power. That's what it's talking about, descending order. Okay, let's talk about that. It's saying that if at most we should have real zeros as many as the number of n's we have. So the n is representing the leading degree. It's saying that we should at most have about that many x-intercepts. Doesn't always mean we will. It says at most we will have n minus 1 turning points. So if my leading degree is 5, we should have at least or almost 5, because there may be times that it wouldn't be true at that point, 5 real zeros, and we should have at most or 5 x-intercepts. We won't have 7. We won't have more than the power. We may have less, but not more. Same with the zeros. And then that means that my turning points would be 5 minus 1 should be at least, or at most, excuse me, not at least, at most 420. Turning points may have less. Turning points on the graph, also called relative maximum. So it's going to be my high point, you know, right? The minimum, the relative minimum. So it's going to be this low point down here. Occur when the function changes from decreasing to increasing. So decreasing to increasing, right? Left to right. Increasing to decreasing, red left to right. So we read left to right on our graph. So to graph a polynomial function, I'm going to just go through these quickly. We're going to use the leading term test to determine the end behavior. So it's going to determine so we have a, let me write this right quick. A raised to the n power, we're going to say a is nth the n subscript. So if a is positive or negative, that affects our n behavior. If our n on the x, right, the leading coefficient, or excuse me, a is the leading coefficient, n is the leading power, or leading degree, whichever one you want to call it. If it's even or odd, that also affects as well. Find the zeros of the function by taking the function and setting it equal to 0 and then factor out. And this would give us all our x-intercepts. Why do I say it give me x-intercepts? Whenever we cross the x-axis, we know that y is always 0. So if I'm going to take a function in respect of x, set it equal to 0, then my y is 0 here. When we cross the y-axis, my x is always 0. Y some number, right? So that's what number 4 is talking about. Number 5, if necessary, find additional function values to determine the general shape of the graph and then draw the graph. As a partial check, use the facts that the graph has at most n intercepts, or n x-intercepts, and at most n minus 1 turning points. The multiplicity of zeros can also be considered in the order to check where the graph crosses or is tangent to the axis. So say we have, let's just do that. Well, that's terrible. I was going to try to make it something else. I'm not going to tell you. It's terrible drawing. So let's do this. So say that I have this function going on like this, and I want to find the tangent line. So right here would give me the tangent of the line, okay? I'm not saying, I'm just giving an example. This is not always where it's going to be at on that function. Okay, so the first one says graph the polynomial function. You're given h of x, so that means the name of this function is h, and its respective x is equal to negative 2x to the fourth plus 3x cubed. So it's written in descending order because the power is 4 going down, right? So we're good. So that means my leading term is going to be the negative 2x to the fourth. That's my leading term, where the leading degree is 4 and the leading coefficient is negative 2. So we're looking at my leading coefficient is negative. So being negative, that's going to affect the way my graph works. And this here being even is also going to affect it. All right. So you may want to go back to the rules from the beginning of the section on negative and even, what it does to the function. However, we know that since it's an even function, we're going to increase left to right. And we have that behavior going on right here. Yeah. And then there's something going on here in the middle. We haven't determined the turning points and the x-intercepts and the y-intercepts yet. And then since it's a negative leading coefficient, my end behavior is going to decrease. Okay. Now, to find the zeros, first, let's just plug in 0 for y. When I do that, I'm going to take that negative 2x to the fourth plus 3x cubed, set it equal to 0, and let's solve for x. Now, when I'm solving for x, I'm going to look at these two here going on the side, and we're going to ask yourself, is there a GCF? And I notice I can factor out any time your leading coefficient term is negative, bring the negative out. So it's a negative 1 times whatever else we factor out. And I notice I have x to the fourth and x cubed. So the most I can pull out is x cubed. When I do that, I'm going to say I'm dividing by that negative x cubed. Okay, so now let me go back to the purple. All right, so now that I'm factoring out x cubed, negative divides negative is positive. X cubed, I'm pulling it out of x to the fourth, leaves me with 2x. Negative, I left that off, my apologies, guys. Negative divides positive is negative, and I'm pulling 3 of the x's out of 3 of the x's, leaving me with 3. So I'm going to take each part, set it equal to 0. And let's solve. So that means I need to divide by -1 here. Well, anytime the numerator is 0, my answer is 0. Let's add the 3 to the side and divide by the 2. So I have an order pair of 3 halves, because that's what x is, comma 0, because I plugged in 0 for y. Now I have this x cubed here. So if I take the cube root of x cubed, it gives me x. That's what we wanted. But we're going to do the same thing, and it's an odd root, so there's no plus or minus. So cube root of 0 is 0. So there's a possibility that I have 3 places of 0. But what I do know in this particular order pair, I'm at the origin. X is 0, y is 0. So let's just check our work. As you notice here that it's already been solved for us. So the zeros are 0 and 3 halves. And we can write it in an order pair. There we go. Now the zeros divided the x-axis into 4 intervals. So if I was to draw this out on the number line, that was let me fix that right quick. Let's draw it just a little bit neater. So if I was to draw it out on the number line, I know this ends negative infinity. This ends positive infinity. 0 would be right in the middle. I know that 3/2 is actually 1.5. So it's going to fall between 1 and 2. And then on this other side, I have negative values going down to negative infinity. So this is telling me from negative infinity, so I'm going to put a parenthesis because you don't ever put a bracket on infinities, to 0. So I have this point here. Oops. Hang on, I keep touching a button on my pencil. Whoops, go back. See if it'll let me do it again. My apologies, guys. My pen's acting. Okay, so let's just skip it. So from here to here, we have one value because look, it said that we have an intercept there. And then let's change this one. From the 0 to the 1/2, well, we have an intercept there as well. So I got 0 to 1 point, or 3/2. Write it back in the same notation, guys. And then, oh, it was X. So my apologies. I got my order pair flip. Let's flip it back. No, that's right. I'm writing it how it is on the number line. My apologies, guys. I'm just writing what I'm seeing on the number line and in that format. Then the next one said, okay, let's go there. 1.53 to positive infinity. So that's where they got this from. Just looking at the number line. Okay. Now, this is telling me, so on an interval of negative infinity to 0, so let's go back to that. On this number line, if I pick some point between here and here and plug it in, well, I'm going to plug in the -1. I'm going to choose -1. You could have chosen -2 and so on. But let's check -1. If I plug in -1 here, okay, so that -1 square, or to the 4th, because it's an even root, becomes positive. So this gives me what? -2 plus, well, that -1 cubed is negative. -1 times 3 is a -3. This is going to give me a negative value. So this is what it's telling us right here. It's saying that when we plug in -1, we get a negative. Okay, it's saying it's below the x-axis. So what if, and it says you can plug in -5 if you wanted to try it out as well. We're just testing points in between here. So the next one says 0 to 3/2. If you pick some point on there, oops, let's look at it. So if I pick a point from here to here, let's pick 1. So if I plug in +1, what do I get? Well, I end up with -2 plus 3. It gives me a positive number. So that's what it's telling us here. So it's above the x-axis. And then let's plug in some point on the other side over here. So from 1.5 to infinity, let's just pick 2. So when I pick 2 and plug it in, oops, what do I get? I get what? -2 times 16 plus 3 times 8. So this gives me -32 plus 24. So I get a negative value. All right. So knowing that, I get a negative outcome. And you can pick another point if you wanted. It's below the x-axis. Okay. So now that's telling me the behavior too. It's telling you how to graph it, the locations of the graph. So just picking those points. Now, we found the y-intercepts. Let's find the x-intercepts. Or excuse me, we found the x-intercepts, right? They were 0, 0, and 3/2, 0. Guys, anytime we end up with a origin as an intercept, we know that it will be an intercept for the other value as well. So Our y-intercept should also be 0, 0, because 0 for y, 0 for x. Okay, so if I plug in 0 for x, yes, my outcome came out to be 0, so that is correct. So we know that this function is crossing the x-axis at these 2 points, and the y-axis also shares the same point because of the origin. Now this is saying if I just was to plug in some values to be able to plot them better on the graph, we could. So you want to plot the intercepts, always plot them. Determine the behavior of the graph based upon the negative and the even value here, and then just plot in some points. And you can check it on your graphing calculator if you like. So it says for any polynomial function p of x with real coefficients, suppose that for a is not equal to b, then the polynomial function of a and the function of b are, and it's p in respect of b, p in respect of a, are the opposite signs. Then the function has a real zero between a and b. The intermediate value theorem cannot be used to determine whether there is or is not a real zero between a and b when p respect to a and p respect to b have the same sign. So here we go. We have, using the intermediate value here, we're going to determine if it's possible that these are functions, so are real values. So what if I took, let's look at this one, this for here. We are giving a value of -4 and -2, so let's do that. We have f of a, and a in this case here is -4, so let's plug it in. All right. So that negative cube, since it's an odd power, it's going to stay negative. And then 4, so we're going to say 4 times 4 times 4 because it's cubed, so it multiplies itself 3 times, sorry, because it's a power of 3. That negative square, since it's an even power, it's going to be positive, and then positive times positive is still positive. 4 squared is 16. And then I have this negative times that negative gives me a positive, and it's 24. So let's do this. Now what I have -64 plus 16 plus that 24 gives me a -24. So now let's take when f of b, which in this case f of b is -2. Let's plug it in. And the negative signs still say true. Oops. Get a little carried away there. All right. So negative to odd power is negative. 2 cubed is 8. Negative squared, which is the even power, is positive. 2 squared is 4. Negative times negative is positive. 2 times 6 is 12. So now what do I have? -4 plus 12. So it would be a 9 or 8. Sorry. 8, because 12 minus 4. Yeah. My apologies. So that took care of this one. So what does that tell me? By the intermediate value theorem, it says that f of -4 is opposite, and let me just finish this out, my statement, and f of -2 have opposite signs. Then f of x has a 0 between -4 and -2. So and if you look, the f of -4 yielded a negative sign, and f of -2 yielded a positive sign. So therefore, we know that there has a 0 between these two on the graph. Okay. And if you'll look, the next slide confirms it. Okay. Now, when we do the same thing for this other one, I plugged in -1 for A, right? We get a positive answer. Plug in +3 for B and get a positive answer. So, since they are opposite sign, or excuse me, since they're both positive and they are not opposite signs, Thus, the intermediate value theorem does not allow us to determine whether there is a 0 between -1 and 3. Note that the graph here shows that there is 2 zeros, but since this outcome came out this way, it's not going to work in this format. And why it's not going to work? The intermediate value theorem.